Yeah, so on your textbook, work energy equation is defined as U122 equals T2 minus T1. We call this work energy equation. Oops. Oh, man, I couldn't spell today. All right. And looks pretty simple, but instead, the equation we're going to use all the time for this course going to be a little bit different than this one. Okay, so instead of just writing U122, the work energy equation we're going to use, you're going to use for your homeworks, for your exams, going to be a little bit longer than this. It's going to change this to T2 plus V2 equals T1 plus V1 plus U122 NC. I'm going to explain each term later, but this is the equation we're going to use in chapter 4B. Okay, first write down that equation first. Now we're going to explain each term. So first, we have, if ignore the T's, V's, and U's. Just look at this. We have the notes there, 1 and 2. What does those mean? Why we have 1, 2 in our equations? They're states. What type of states? Initial and final. So here, yes, they represent two different. In this section, I want to replace the word state with position. So in this section, we're talking about particle moving at different positions. So 1 and 2 represents that particle either at position 1 or position 2. So that's why we have 1 and 2. So on the left-hand side of equation, we have T2 plus V2. That means it's everything at position 2. At right-hand side of equation, we have everything at position 1, T1 plus V1 plus U122. Okay, now let's take a look at what is T and what is V and what is U. So T, in this case, T, it's kinetic energy. So T2 is the kinetic energy at position 2, and T1 is the kinetic energy at position 1. So that is kinetic energy. Okay, something is different here. We have been talking about velocity, acceleration, forces, but we have never talked about energy. Where did you learn energy? Which course you learn energy, the term energy? Thermodynamics. Did you guys learn anything about energy in physics? Okay. Do you guys still remember how to calculate kinetic energy? 1/2 mv squared. Yes. So that's how you calculate kinetic energy. That equals 1/2 mv squared. So kinetic energy, it's a function of mass and speed. So how to calculate kinetic energy at position 1? If I have a particle, this is my particle. I move this particle from position 1, which is right here. It's statics, it's not moving, but I start adding a force, pushing this particle moving. This is position 2. And what is energy, kinetic energy at position 1? When it's not moving? That's 0, right? V is 0. So 1/2 mass times 0. And at position 2, that particle has a certain speed. So we just need, in order to calculate what is kinetic energy, T equals 1/2, mass doesn't change, V2 squared. So plug in what is the speed at position 2. Okay, that's T. It's kinetic energy. Let's look at what is V. In this equation, V, we have V1, V2. V is potential energy. Anybody knows what is potential energy? Yeah, you heard gravitational potential energy. So imagine this is my particle. If I just, well, no, we'll just put this on the table. I'm not moving it. It has 0 kinetic energy. But what is the potential energy for this particle, for this remote control? Okay, maybe that's a good question. Give you 1 minute, talk to your neighbors to find out what is the potential energy for that remote control right now. Okay, what is the potential energy for that remote control? Cameron? It's height. What is height? Can you say it loud so everybody can hear? What is the height you want to use to calculate potential energy? Yeah.
The top of the ground. So basically the distance between the top of the ground and the bottom of our boat.
Okay. Any other answers? How to calculate potential energy for this guy? Bethany? Do we have a spring here? Yeah, that's well, we haven't talked about that yet, but yes, we do have the equation to calculate spring potential energy. But what if we only have this remote control right here? Yeah, then how to calculate G times what? H. MGH. What is H? Which height? It's my height? The table height? Everybody agrees it should be the height from the remote control to the ground we're standing. Raise your hand if you think that's a height. Okay. Because someone who disagree with that. Okay, Nicholas, I didn't see you raise your hand. So what do you think should be the height to calculate potential energy? Wait, say that again? The height of the remote control itself? Okay, so we have different answers. And where are we on the first floor? Is this the first floor? Do we have a basement? What if somebody is in the basement and they're looking at that remote control? What is potential energy respect to them? What is potential energy? Who can tell me that? Ella? If you're in the basement, you're looking at this remote control. Wow, if you can still see it, what is potential energy?
Is the floor still there? Like, is it gonna stop moving at this floor?
No, it's just sitting here. We still have the floor, but you are in the basement.
I feel like it's still be the same height of where it is from the remote to this floor, because it's not gonna keep moving like that.
Okay. Okay. Now what if we drill a big hole here so we can drop all the way down to basement? Would that change its potential energy? Okay. So potential energy has nothing to do with if we have a hole, if this guy can move. Potential energy, it's a energy that must be referenced to a reference point. So all the answers you tell me are right. So you said, okay, potential energy, the height can be calculated by at its own height of this remote control, or it can be calculated by using the height of that table. They're all right because you're taking different reference points. If my reference point for potential energy, for gravitational potential energy, it's right on this table, then my answer for potential energy for this remote control is 0 because it's sitting on my reference point. There's no potential energy. Does that make sense? And if my potential energy, as said, this ground, this 4 is my reference point, then the potential energy of this remote control is going to be the mass times g times the height of this table. And if someone's in the basement, they think the basement is the reference point, then the potential energy of this remote control is, what's going on? It's the height of that from this floor to the basement plus the height of that table. Now we're back online. Okay. Now what happens if someone's in the rooftop of this building? And what's the potential energy for this remote control? Look. Yes, would be negative potential energy. If the guy in the top floor, the rooftop, they think the roof is the reference point, then this remote control has negative potential energy, and you have to use the height from this point all the way to the rooftop. Then the potential energy is going to be negative mgh, right? So the potential energy really depends on where you choose the reference point. So that's for the gravitational potential energy. I have a question. I need help. How to spell gravity again? Gravity. Is that right? I'm not very confident with my spelling. All right. So that's for gravitational potential energy. And V equals Let's call this VG, mgh. So if we go back to look at inside of this equation, how to calculate potential energy from gravity at position 1, 2. You need to set up your reference point, right? Depends on where you set up your reference point. And you have to calculate your potential energy based on your reference point. Okay, so that's the potential energy from gravitational force. We can also have potential energy from spring. Spring, if you have a spring in the system, that gives us potential energy as well. Bethany, now you can tell me how to calculate spring energy, potential energy. K X, let's call it V spring, equals Kx what? That's it? Okay, let me double check. So for spring, who else know? Do you guys have a different answer? How to calculate potential energy from a spring? We're pretty close. To calculate potential energy from spring, we definitely need the spring constant K, and also the X, which is the deflection in the spring. But the correct equation for that is this. For spring potential energy, it's 1/2 K times delta X squared. So that delta X, it's a change of length when you either compress the spring or stretch the spring. K, it's a spring constant. So that's how you calculate potential energy from spring. Depends on how the length of the spring is changed based on its original length. If you compress the spring, well, hey, question here. For gravitational potential energy, we have either positive potential energy or negative potential energy. Depends on where we set the reference point, right? Everybody agrees with that? Yes, that's the truth. For spring potential energy, can we have negative spring potential energy? Can we? Raise your hand if you think we can. Negative spring potential energy. It's impossible to have. We can have 0 spring potential energy, but it has to be always positive because you have that delta X. Even delta S is negative, but you take a square, everything is positive. So we only have 0 or positive spring potential energy. So this guy is always greater or equal to 0. Okay, now you already see that we have under potential energy, we have 2 different types of potential energy. So how to calculate V1 or V2? So V1, it's a potential energy at position 1. To calculate V1, you need to consider both gravitational potential energy and spring potential energy. So V, to calculate that, V need to be equal to Vg plus Vs at any position. Well, it depends on the system. Sometimes we don't have spring. Sometimes everything on the same level, so we don't have to consider gravitational potential energy. But to calculate potential energy, it's a sum of gravitational potential energy and the spring potential energy. Any questions here? Right, Now let's move on to the next term. What is this guy? U122 NC. This term represents the work done by a non-conservative force of forces. Okay, so this UNC 122 represents the work done by non-conservative forces from position 1 to position 2. That's confusing, right? What do you mean work done? How to do work? Okay, if imagine this is my remote control on the table, how to do work to this remote control? 1 minute, talk to each other, how to do work to this remote control. Okay. Okay, how to do work to this remote control? Hunter?
You have to move it,
Move it. How to move it?
apply a force to it.
Apply a force to this remote control. Now what is happening? If the remote control is moving, then you are applying a work to this remote control. So how to calculate work? No, that's this question again. If I'm applying a force, a very tiny force to this remote control, and well, if that force is smaller than the friction force, the remote control is not moving. Am I doing work to this remote control? No, I'm not. Only if this remote control moves, then I can say I'm doing work. So how to calculate work? You know, you have to have a force. What is this other component? Yeah, it has to move. So instead of velocity, we say it's a distance. So you apply a force times the distance it moved, it traveled. That's work. So let's do that. Work, it's calculated by force times the distance as it traveled. And on your textbook, also writes that the work done by non-conservative force equals integration 1 to 2, and that's force vector times et hat ds. So it's the integration over distance. And that et hat represents the direction. Remember, in path coordinate system, et hat represents the motion, the direction of motion. So a more accurate calculation would be use a force vector times the direction how that particle is moving. But in most of the cases, it can be simplified to just force times distance it traveled. For example, if we have a let's see that. If our floor is not flat, we have a particle right here. We can apply a force to that particle. Let's call that particle A. This particle A is going to move along this curved surface. And when you calculate the work done by that force, it is force times the total length of that curve, S. That's how you get the work done by that force. Okay, now let's talk about what is non-conservative force. So that's a kind of weird concept. What do you mean non-conservative force or conservative force? But that's something you have to take a note, remember it, memorize it. So in this course, the non-conservative force you would say in this chapter, it's friction force. And if we have other situations, we can tell you which one is non-conservative force. But friction force would be the classic non-conservative force in this course. Right. But at least I can tell you what forces are not non-conservative force. So we have another type of force. It's called conservative force. So that's we have gravitational force, spring force, and yeah, so all the weight force, all gravitational force, and spring force are conservative force. And this equation, or this UNC 122, it's only for non-conservative force, such as friction force. That's the one we just mentioned. Another non-conservative force would be you're manually adding a force to that particle and moving it into a certain path. And that would be considered as a non-conservative force. So it's, let's see, besides friction force, additional force or external forces. Okay, so now so far we talked about T, V, and UNC 122. That's all the components inside of that equation. Okay, now let's see if we have time to do a practice. Maybe next time. Okay. So that's the equation. Now let's talk about the steps in this section to solve problems. Remember previously we have 6 steps approach for each section under each chapter. So for the same thing for this section. For B, we have to follow certain steps to get the solution we want. So let's talk about the steps we have to follow. Okay, the steps in this section is going to be a little bit long. So remember what we did in section 4A, the 6 steps? So here we're going to have step 1, it's free body diagram. Step 2, it's set up coordinate system. Step 3, it's forces in vector form. And step 4, it's acceleration in vector form. And step 5, assemble F equals ma. And break it down to scalar equations. All right, so the first 5 steps are exactly the same as chapter 4A. So exact the same steps from chapter 4A. Nothing's new in the first 5 steps. But here something's different. In step 6, we have to build a table for kinetic energy for each mass. So here it's important, it's for each mass. Remember, if we have multiple masses in the system, each mass is going to have kinetic energy based on its speed. So we need to build a table for that. So my expectation for this for you is you want to have a table with 3 rows, T1, T2. The first row going to be mass. You're going to list different masses, mass 1, mass 2, depends on how many masses you have in the system. And under each mass, you're going to calculate what is the kinetic energy. So that would be the equation for kinetic energy, going to be just 1/2 1v1 square. That's mass 1 at position 1. If you have mass number 2, same deal, 1/2 m2 v2 square. Sorry, that's v1 square. The only thing difference is M2. At position 2, the kinetic energy at position 2 is just M1 half M1 V2 square, 1 half M2 V2 square. So that's what do I mean? Build a table for kinetic energy for each mass. So that's step 6. Step 7 is to table for potential energy. Okay, potential energy, the symbol for potential energy is V. So we have V1, V2, okay. So the first row going to be different types of potential energy. And we have talked about, we have 2 different types of potential energy, gravitational potential energy or spring potential energy. So you're going to list this. So the first one going to be, let's see, gravity potential energy or and spring. If we have other potential energies, you're going to list all of them. So under each potential energy, you're going to calculate what is that potential energy at position 1 under this row. Under gravity, that's going to be just mg h1. That's the potential energy for gravity at position 1. At position 2, that's mg h2. If you have spring, we just introduced that equation. That's 1/2 k delta x1 square. Delta, that's at position 1. At position 2, you're going to have 1/2 k delta x2 square. Okay. And that's step 7. Step 8 is to have a table for work done by each non-conservative forces. Okay, so what are the non-conservative forces? If we have friction force, that's going to be there. And if we have external force, that's going to be there too. Depends on how many external forces you have. If you have multiple ones, then you have to do that for each one. Let's do that if that's called. Let's call that F1. Maybe perhaps you have F2 in the system. Then you have to list F2. So to calculate work done by non-conservative force, the equation is pretty straightforward. You can use force, that's friction force times, let's call this FF, times the distance is traveled. And for the any external forces, you're going to have just F1 times the distance, or F2 times distance. That's F2. Okay. So far, by the end of step A, you should have 3 tables with kinetic energy, potential energy, and work done by non-conservative forces. And step 9 is to assemble the equation. Use the equation. That's T2 plus T V2 equals T1 plus V1 plus U and C122. Now you need to assemble everything from your table into this equation. So if we look at an example, V2 inside that equation must contain whatever is under V2. So for this table you have, V2 has this term and this term, so you add both terms for your V2. And same deal for your V1. V1 should be your MGH1 plus that 1/2 K dot X1 squared. That's your V1. And same deal when you plug in T2 and T1. You need to do T1 equals the sum of the first term plus second term, and T2 equals the first term plus second term. Same deal for your non-conservative forces work. That U1 to 2 and C equals that work plus that work and plus any other work in your table. So that's what I mean, assemble everything into that equation. So once you have this assembled in step 9 to the equation, you're able to solve unknowns. So one key difference here is if we look at that equation, do you see any vector notation? Yeah, that's probably the only time in this semester I don't have any vector notation in a equation. So that tells you this equation, it's a scalar equation or vector equation. It's a scalar equation. So that's a scalar equation. At step 9, you're building just one big scalar equation. Then you use that scalar equation to solve some of the unknowns. The unknown could be the mass, or speed, or spring constant, or spring deflection, stuff like this. But most commonly in this section, you're looking for distance. How far a block would travel, what's the deflection of the spring. So a lot of questions ask you the distance. Okay, do you have those 9 steps writing down on your notes? Yes, so for each problem, you have to follow all 9 steps. That's why this chapter is, this section is a little bit hard to do. It takes a lot of time to go through all the 9 steps. Making notes here for this equation. This is a scalar equation. All right, that's the intro for your chapter 4B. Any questions? Make sure you start your homework early. And if you have questions, feel free to come by to my office and ask questions. That's all we have today.